Good evening, everybody. My name is Eric Aguilar. I am an Assistant Delivery Manager for the Mars 2020 Sample Caching System. And so, but I've been at JPL for about 16 years. So I'm going to talk a little bit of yesterday, today, and tomorrow based on some of my history there at JPL. I will cover some of JPL's history too, but although I am a bit of a history buff, just not all of JPL. So, the big thing is I do like questions. I love questions because I want this to be as much as about you as it is about me. Like I said, I've worked at JPL for 16 years. My first mission there was a Mars Exploration Rover, which is Spirit and Opportunity. I started there doing electronics design. Eventually walked it all the way through until launch, into operations. And then I moved on to work on Dawn, which is a Deep Space Explorer, which is we went out to the asteroid belt to measure basically what, if you guys are familiar with the way the solar system is, right? You have Mars, then the asteroid belt, and the asteroid belt is where essentially scientists feel that there should be another planet, right? That's about the same area. So what happened there? So Dawn went out there to go, sort of dawn at time, right? Go out there and look to see what happened out at dawn. And there I designed part of the DCIU, which is the Digital Control Interface Unit, which is all of our gimbal drives and thrusters to actually get us there. And then now, then I went and started working on Mars Science Laboratory, which is a Curiosity rover that's currently roving on Mars right now, and actually Opportunity is still roving on Mars. But Curiosity was my latest mission there, and there I was responsible for doing all of the integration and tests at the system level. So we actually brought in all the avionics, all the hardware, all the software, put it all together for the first time. My team and I were responsible for testing that and making sure that it worked as well as it did. And then now I've moved into the Assistant Delivery Manager position for the Mars Science Lab, Mars 2020 for the Sample Caching System. Now, I don't know if you guys have read up on what the Sample Caching System is. What we're planning on doing, this is step one of a sample return. So our plan is to actually get to Mars, rove around, determine based on our science which type of rocks we would like to take samples of, and take a sample from the Martian surface, hermetically seal it in a tube, and then have a future mission pick it up and bring it back. So this is sort of our step one there. Okay, so I'll get into some more details to go along, but I'm gonna start walking through a little bit of history and why I think it's important that we have some of our history from JPL. But JPL, if you guys don't know, we're over there in La Cañada, just 2 miles north of the Rose Bowl, and we have about, I think now we're up to about 6,000 or so employees. So it's a campus. It's pretty much a campus like you see here, right? It's a pretty nice setting. And we're a federally funded research and development, so we're one of NASA's 10 centers. However, we're managed by Caltech. So we got this weird thing where we're government for some times, and then other times we're the school, and I think it all depends on what kind of benefits you want to give us. If you want to get a day off or not. So that's kind of the hard part sometimes. So every time you'll see NASA, JPL, and Caltech, it's because we report to both of them at some point. So a little bit about JPL, sort of why did we start, how did we start, right? 1936, there was this notion of what they called the Suicide Squad. What it was actually a bunch of Caltech students, and that's kind of where Caltech got into this business, right? Is some Caltech students were working on rocket fuel. Actually caused a problem in their dorm room. Caltech got a little upset, right, and said, "Don't do it here. Go out there in the arroyo and do it out there in the arroyo." And that's basically where this is taken at, right? I always laugh at this picture because it's sort of the way when I've looked at this in the past and I've read some specs on this, and they said that those sandbags, that was their protection from the rockets that they were launching. It's pretty close. It's not like that far away either. So I thought, okay, that's one way to do it, right? We're actually a lot safer now when we do stuff. So they make sure we have to do a lot more training and that kind of stuff. But actually, this sort of spirit is what embodies the people at JPL, right? We tend to try to do things that have never been done before. That's essentially what these guys started off to doing, right? And so sometimes it's like, yeah, things may not go as right as we want. So we learn a lot from our failures, and they certainly sort of started this tradition that we have now, and we try to keep it going. A bit of a better picture, but you can see that it wasn't all that much protection there from launching a rocket. And so, one of the, early on, JPL was established in 1943. It was actually one of the divisions of the Army. And as of recently, actually, we had one of our colleagues actually just passed away not too long ago. But he actually started working shortly after JPL was established. So he was a JPLer for 62 years, right? And so it was tough to see him go, but he actually had a pretty long and fruitful career. I learned a lot from him going through that. And so JPL really kind of got thrown into the fray when Russia launched Sputnik. And so our response to that, or essentially the U.S.'s response to that, was to get something in orbit. January 31st, 1958, Explorer 1 was launched. And you can see there, it's just a little guy, but it was the first time that we were able to get into orbit, right? So we actually put something in orbit, and that was our response to Sputnik.
At the National Academy of Science, exhausted as they were, the trio obliged with what was to be the page one spread in newspapers all over the world. In plain language, the United States was in the space business along with the Russians, and Explorer 1 was the beginning.
So we've essentially, since then, right? We've been working towards, pushing the boundaries, right? So we went from Explorer 1 as a sort of response to now let's get to the moon, right? So now we start looking at how do we get to the moon, but we do robotics, right? So one of the big things about JPL is all of our stuff is robotics, and in order to, anywhere we go, we tend to send the robot first, right? Because we don't want to put a human life in danger until we understand where we're going. So just about every single time, right, JPL is in the forefront of sending robots, sending satellites to actually go do observations, imagery, and getting things back. Okay, so that's kind of where we line up with NASA. NASA is broken up mainly in robotics, science instruments, and human space flight, right? We typically stay right in the robotics area. So most of our stuff you'll always see sort of robotics is our background, our sort of forte, and the rest of NASA can handle the manned stuff. But typically that's what we do is we start launching and start understanding what happens at the moon, so we can then help prepare the astronauts going forward. So getting a little bit to where my history starts to kind of come in, right? So a little bit of Viking. Viking was the first landed mission on Mars, and essentially that's what sort of really kicked off the sort of Mars program. Started off early on to get there, and similar thing, right? It was one of these where we had to orbit around, and then we decided how to land this thing. So when we got Viking there, that's sort of the first time we actually landed on Mars in 76, 40 some years ago. The big thing about that is that we sort of stopped after that, right? There wasn't a whole lot of what else do we need to do to get to Mars, right? Because now it's like, yeah, we landed, we're able to explore, we're able to just land and not actually do too much roving. Not until, I'm gonna scoot ahead a bit. Not until Mars Pathfinder in '97 did we actually go back and feel that now we have an opportunity in technology to help us actually explore Mars a little bit, right? There's one thing about landing, but you're in one spot. I can only reach kind of as far as my instruments can, right? So I can't do too much. So Pathfinder was the first time for us to actually rove and actually explore a planet by driving around. So Pathfinder 97. I think there's a little video here. So Pathfinder came in, and it was a balloon landing, right? So the way it comes in is as we approach getting into Mars, we have a parachute that slows us down that's going at Mach 1, right? And then eventually we have some rockets that help slow it down a little bit more, and then we have balloons, right? Big airbags. Now these airbags fill up the room, right? If it was to actually probably twice this height. Typically, the first bounce on these airbag balloons is about 9 stories. When you yeah, it's coming in fast. It's coming in fast and it's bouncing hard, right? So that was the first set, right? Eventually, it kind of settles in. It's just a big giant ball, so it kind of bounces around and eventually stops. Then we deflate the bags and we pull it in. We pull in all the airbag material, and then the lander opens up, and we allow Pathfinder to kind of go out and explore. I think this one only had a couple different science instruments. So this is our first go at let's actually get some remote science or contact science that we actually can do on Mars. And it had this thing is probably the size of a kind of a microwave today. It's not very big. All right. So
question?
Yes, sir.
How did you make sure that when the lander landed, it was in the right position so it could roll off?
Oh yeah, that's a good question. So we actually don't count on that to happen. So what ends up happening is that we have sensors basically inside the lander. In this case, the sensors are on the lander, and that tells us what orientation we landed. So if we land on our side, the motors can actually push on the side panels and kind of flip itself back over. So we actually created algorithms to do basically a little bit of a dance to get it to right side up, and then we open it. So we knew there's no way to control that.
Right.
So the one that was interesting is if you actually land point up, right? This is almost like like a pyramid. And if you land point up, then that was a funny walk that it had to do to get it to kind of fall over. But eventually, yeah. So we actually purposely knew that was not going to happen. So we designed it, and we designed algorithms to do it on its own. Good thing is, so one of the things that we did is it's a good point, right? Is we have to think about stuff that's not happening. So one of the challenges with Mars is not only the environment that it's in; it's a fairly extreme environment. But it's the fact that communication can take up to 22 minutes round trip. So the rovers have to be autonomous. We cannot joystick them from the ground, because if I tell it to go, it's 22 minutes before I know that I got to stop. Another 22 minutes before it goes back there, and by that time I'm done. Yeah, I crashed or went over a cliff or something like that. So yeah, so absolutely. So a lot of the things that we do, we have to actually build the autonomy into the robot itself to actually do this work. More questions? So then we get to some of the cool pictures. This is it. This is the Pathfinder rolling off.
Well, it's my distinct pleasure to present to you the first rover on the surface of Mars. The images that you've seen today show a completely deployed rover that has driven down a perfectly deployed ramp and gotten to the surface of Mars, making its first tracks in the soil of this new planet. And to us, it's opening a new era.
So if you've seen The Martian, this was the thing that saved Matt Damon, the rover. But if you actually look at it, it was actually a really good representation of it, right? The mast. The reason you're able to see the rover drive away is because the camera mast is actually on the lander, not on the rover. Okay. So then we're gonna. So now we're gonna get to something that's near and dear to my heart now, right? Is Spirit and Opportunity. So this is my first mission at JPL, and as you can tell, it's actually, well, maybe you can't tell from here, but it is bigger, right? This is now the size of about a golf cart. This rover can. This is a Spirit and Opportunity. So this is twin rovers. At the time when we decided to do twin rovers, it was we're going to send two because Mars was taking about half the missions going to Mars. So you were losing about 50% of your missions going to Mars. So we thought, well, let's beat the odds. Send 2. At least one's got to work, right? And so we actually sent 2. So we actually had to build 2 flight units. We launched them about 3 or 4 months apart, and I think they landed about a few weeks difference. So Mars was still getting closer as we launched the second one. This one came now with, we decided to actually get away from our lander that had most of the electronics and put them all on the rover so we can actually get some more roving out of it. This rover was actually designed, or it was designed, you know, with our best engineering practices, but it was designed for a mission life of 90 days. That was in 2003. It's still running, right? So it's still going. We've lost one of the rovers. We've lost Spirit. Spirit was in. So one thing that we learned about Mars is that there's some soft sand areas, and so what we do is we designed a rover to actually drive around and get with autonomy to see where things are going. And then we got to a field or a clearing, and we said, you know what, let's really make some treks here. Let's get some distance on it, right? So we told Spirit, just go for like a good 10, 20 meters, right? So Spirit said, okay, I'm gonna go for 20 meters. I'm not gonna, because there's nothing in front of me, there's nothing for me to worry about. So I started driving, it spun its wheels for 20 meters and stopped, and it radioed home, and we said, well, that doesn't look right. And so it turns out that it was on a really soft sand. I don't want to call it quicksand, but it was something really soft that as it started to turn the wheels, the rover started to sink. It started to drive itself in. So, you know, so what do you do then, right? So we have to figure out how to get it out. Now it's on a different planet. You know, you think about getting stuck on the side of a road. How about another planet where you got to figure out how to get something out? So the good thing is the rover was in a good area where we actually got plenty of sun, so the heaters were able to stay on and work. And so we eventually figured out how to kind of get the wheels to kind of turn, and you know, we actually recreated it as best as we could. We talked to a bunch of scientists, and we came up with a sand mixture, and we actually created a big giant pit. And we always keep one of these rovers behind as our engineering model, so we can test with it on the ground and actually see how it's performing. And for the options that if something ever happens, we can actually try to work on it, right? So we actually created this big giant pit. We filled it with sand, clay, and diatomaceous earth, you know, stuff for your pools. And we got it real fluffy, and we actually buried the rover in there, and we're able to drive out. So we thought, okay, now we have some sequences, we can send it, have it drive out. And that was pretty cool. It came out. So we said, oh, great, okay, now let's keep going. You know, let's try to be a little more careful. And well, lo and behold, a few months later, we get stuck again. Right, the ground is just too soft for us, right? We thought the wheels were wide enough to actually get us past that stuff, but nonetheless, we got stuck again. This time though, we couldn't get out. We thought we knew how to get out before, let's do it again. Turns out we actually we have an imager in here at the end of the arm, and we took some images underneath to figure out if the wheels were not just, why aren't they getting unstuck? And you can actually see in some of the imagery, there's actually a high point. There's actually a rock that's right in the center. This thing is all pretty low, and there's a rock that's kind of holding it right there, so it just won't let it go. So eventually, Spirit, in the angle that it was toward the sun, wasn't able to keep the batteries and the heaters on, so it eventually just sort of froze. Yes, sir?
So most of what we're seeing is the solar panel that powers it.
Yes, up on top.
So is there any mechanism for blasting it off and cleaning the silt off the panels? Or?
So yeah, the dust devils on Mars. So apparently we got extremely lucky, and that's why the rover was planned for 90 days, mainly because we thought the dust accumulation was going to be so heavy that it was going to eventually block the solar panels. Turns out that because the low humidity, you know, the sand that's actually moving is not very, very dense. And there's dust devils that actually are sort of natural cleaning of the solar panels. So we actually haven't lost that much power. What happened is that where we were near a crater wall, and we had an angle towards the crater, right, away from the sun. So we're in a big shadow, so we could no longer keep the survival heaters on. And eventually this thing freezes because it gets pretty cold. Right, so we got into a point, now we try to always land near the equator so we get as much sun exposure as we can. But eventually this thing froze, right? And so the electronics won't run. Yes?
How's that thing even get up there?
So it's this, so this was also, you remember the, let's see if there's a picture for that. Actually, there's a video, let me show you the video. So the video will show you, it won't show you the launch, but it'll show you the landing, right? So usually, I think this is a Delta 2 rocket, and we launched out of Florida, Kennedy Space Center. And then I'll show you what the landing looks like.
Spacecraft reporting that heat shield has indeed jettisoned. Lander separation event has been detected. Speed of 173 miles per hour. Expected retro rocket ignition on my mark. However, we currently do not have signal from the spacecraft. Deep Space Network tracking stations in Canberra and Goldstone are still searching for the primary signal.
So this is how this one landed, right? This is similar to the other one. It was airbags, right? These airbags were the ones that were stopping and slowing us down. Again, really high bounces, right? Eventually stopping. And then we have the rover that actually has an unfold. Again, depending on the algorithm, we'll rotate our orientation. We'll unfold, and then we'll take a bunch of pictures, right? And typically, although it showed it fairly quickly, the initial one probably took about a week, 2.5 weeks for us to actually drive off the ramp. Because one is we're going to do a check, right? We just bounced. First bounce was 9 stories, so we kind of want to make sure things didn't rattle off, right? So we want to check that out. So we're going to take some images, and we have a commissioning process that we did to make sure the rover's good to go, and then we actually pick a path to drive off, and we drive off the lander.
Wasn't there an issue with one of the airbags too? Can one of them get wound in all the way?
Yeah, actually it was. It didn't come in as far as we wanted it to, right? But we put different. So we actually do put different egresses off, so you can always turn in place and drive off in a different spot. And I think that's what we eventually did. I do remember testing where we actually pulled some of the airbag material away that didn't, as best we could tell based on the images. Pull it away to actually see what happens on the wheels. So the wheels, right, Pathfinder, the wheels were like these very sharp kind of cleats that, kind of really dug into the ground. I think that would have been a problem if we would have did it on this one. These were actually sort of smoother. We had grazers there that allowed it to kind of come off, so it wasn't too bad. But yeah, I remember us actually pulling some stuff out and trying to see if we actually bound the wheels up, trying to get off. Turns out we don't think it would have done it. We just said, why go the hard way if we can turn around and go the easy way? So we actually went off the easy way with the lander. And then they both started their science missions. Questions? Yes?
How did you test those big balloons that they would?
Oh yeah, so we would we did a lot of different tests with that. We actually we would actually blow them up, right? And one thing what we end up doing is we have to make sure we convince ourselves that we're doing the right test conditions, right? And so one of the things is we would get a reduced mass because the Martian weight's much less than it is on Earth, right? So we're looking at about 40% when it is on Earth. So we would actually get reduced mass, but then have the balloons blow up. And we would actually, unfortunately I didn't bring it with me, but we actually have some test video of some pretty jagged rocks that we set up like on a sidewall, and we just let this thing kind of fall down, and sort of kind of get scratched up and see what happens. And then we keep doing it, and then we try to run models to help us get to, we can't do every single scenario, but we try to understand models and what the soft goods are made of and how strong they are to get us to say that we think we're okay. And any other questions? Yes?
What if one of the airbags pops?
So yeah, that's a good question. If it pops, hopefully it pops after the first bounce, because I think we would have survived after that. So there's a lot of airbags in there, and so if one of them popped, we think we're okay because they're isolated from each other. So we think we're okay there. But that kind of leads me to Curiosity. And Curiosity is one of the rovers on Mars now. And Curiosity, as you can tell by some of these pictures, right? This is a cruise stage as it's entering into the atmosphere, Martian atmosphere. This is the jetpack that we rode on coming down, and this is what we call the sky crane. And what happened is we started looking at the balloons, and we said, hey, balloons, this thing now this rover is about 1 ton, 2,000 pounds. So this is about the size of a small SUV. The balloons can't hold that anymore. They will pop if they come down on the balloons. So we had to come up with a new way of doing it, right? We had to figure out what's the best way to do this. So we came up, whether people feel that we're crazy or not, we came up with the sky crane, right, to actually do it. So let me run the video real quick.
Things are looking good. Coming up on entry. Vehicle reports entry interface. At this time, it will begin pressurizing the propulsion system to increase the thrust of the system. We'll use that for all the maneuvering in the atmosphere we're about to do. We are standing by for guided start of guided entry. We are beginning to feel the atmosphere as we go in here. The vehicle has just reported via tones that it has started guided entry. At this time, the vehicle is beginning to steer its way to the target. We have seen peak deceleration. It is starting its first bank reversal. It is reporting that we are seeing G's on the order of 11 to 12 Earth G's. Bank reversal 2 is starting. We are now getting telemetry from Odyssey. We should have parachute deploy around Mach 1.7. The parachute is deployed. We are decelerating. Heat shield has separated. We're found the ground. We're down to 90 meters per second at an altitude of 6.5 kilometers and descending. Standing by for backshell separation. We are in powered flight. We're at an altitude of 1 kilometer descending. Standing by for sky crane. Sky crane has started.
Signal to us, you remain strong.
Touchdown confirmed. We're safe on Mars. Time to see where our curiosity will take us.
Got thumbnails.
Today, right now, the wheels of curiosity have begun to blaze the trail for human footprints on Mars. This is an amazing achievement.
Well, today on Mars, history was made on Earth. The successful landing of Curiosity marks what is really an unprecedented technological tour de force. It will stand as an American point of pride far into the future.
Well, tonight was a great drama that was played. I could only think of the words of Teddy Roosevelt as I was sitting there. It is far better to dare mighty things even though we might fail, than to stay in a twilight that knows neither victory nor defeat.
So you saw the landing, right? This one's a little more dramatic with the music and all that, but you know, it was pretty hairy when you see all the stuff that actually has to go right in order for this thing to land.
Do you know why they decided to use the sky crane instead of just a soft landing? Because you have the rockets there doing it, and you added a whole new procedure that had to be added on to the end of that.
Right. So it was part of it was contamination, right, of the area. We're trying to minimize how much we're contaminating or.
But you're going to be driving off.
Yeah, absolutely. But there's also a lot of stuff that gets blown back up at the rover.
Okay.
And so between contamination, sort of fog coming back up, right, just rocks and everything showing up.
Oh, so it's contamination of the vehicle, not of the ground?
Right.
Okay.
Yeah. Because we have science instruments that have to be calibrated to run, and actually there was one of our weather instruments actually did get damaged a little bit on landing because some of the rocks.
What's the distance of that cable in reality?
I want to say, I can't remember exactly for sure, but I want to say about 3 to 4 meters, so about 9-12 feet. Okay, so it's not that far down, right? But we still had to drop it down.
The process took what, 7 minutes?
No, actually, so yeah, that's the internet video, right? The 7 minutes of terror that they get you on, and it's a cool thing, right? But actually, from when you separate from the cruise stage and you get to the top of the atmosphere, it's actually about 25 minutes coming in. They took the 7 minutes from a certain point during that entry. I think they actually took the 7 minutes from about when the parachute deploys. Well, in my opinion, that's when we know that's going to work, right? To an extent, we know the parachute's going to come out, and the next 7 minutes is when that's when we start hitting the power descent, to come down, start to drop the crane, drop the crane down to lower it. Now it's going to be the same way we actually fly our next mission, and we're going to actually fly it the same way. It's roughly about 2,000-pound rover. But we're going to have a whole new science suite on there. And so yeah, the 7 minutes, and part is that, right, it lands. And actually even everybody in the room, I'll give away the big secret, right? We shut off all the transmitter to the rover an hour before we actually start anything. So because we actually don't want to accidentally send something to the rover that tells it not to do something, right? So we actually purposely kind of close ourselves off and say we're not going to talk to you, and we're going to shut off all communications. But the rover's programmed and designed to land on its own. Now, one of the cool things, if you guys can find all of our images are posted, but if you can find the first images, the first thumbnails that came down. So what we did is actually the engineers there, we try to have a little bit of fun if we can. But one of the things that we did is, so you notice that when it dropped the lander, the rover, it cut away, and then you see this thing kind of fly off the sky crane, so it flies off and it crashes, right? So it's gonna go off and crash somewhere. Well, we knew that that's gonna cause, or we expected some kind of explosion to happen. So what we did is we said, well, we know we're gonna land in this direction, and the sky crane's gonna fly out this way for about 1 kilometer. We know what that, more or less that calculation looks like. So we took our first picture just as this thing exploded when it crashed. So if you look at the thumbnail, and a lot of people don't notice that there's this big kind of cloud. Now it's hydrazine, which doesn't burn quite like it would here on Earth, right? Because the lack of oxygen, or the low traces of oxygen. But it nonetheless it did have a cloud sort of effect. So you can kind of see it in black and white. But we didn't quite mention that that's what you're actually looking at. It's an explosion off on the side, but we have something that we calculated and try to figure out, can we time this picture just right? So we got pretty good. So we actually caught the explosion. Questions?
What's
when you're looking at this, it's already happened, one way or another.
Right.
The deed is done.
The deed is done.
Is that a weird feeling while you're watching
yeah.
this, knowing that it's
yeah. All you can do is all we're doing is watching the feed, right? It's the news feed. You're hoping that it has an ending. You're hoping that it doesn't. Your telemetry just doesn't stop. Because I mentioned earlier, right? It's 22 minutes round trip. So in round trips, that means 11 minutes coming back. So it already started sending by that 7 minutes, as you said, right? It already landed. It's all we're hearing is sort of the replay, right? And we're hoping that the data keeps coming. And depending on as you're watching the video, you can actually see one of the guys. So part of it was we said Al, the guy that was talking the sort of voiceover, we said Al's the guy that's going to say we're on the ground, right? He's going to give the final telemetry. But there was another guy off in the corner, and his job was to watch that. So we had 2 computers that were flying, right? So as this thing, 2 computers were on at the same time, and one was in charge, and the other one we actually called it second chance. So what we did is we actually had a piece of our normal software running, and then we had this other computer that was looking at this one and saying, well, as soon as you hiccup, I'm taking over, and then I'll land us, right? And we stripped out sort of all the extra flush. This was our sort of Hail Mary, right? If something really bad happened, we're going to take over and land. So the first thing that happens when you land, if the primary computer is still on, the first thing it does is turns off its backup and says, well, I don't need you anymore. So there's one guy in the corner, and his job is to watch the backup. So he's watching. And he gets the indication that, hey, the backup turned off. So he knows, hey, I'm on the ground, right? But this is before Al can say, hey, we're touchdown. So he does it. He's kind of like tense up and ready to go. And then it's like, oh. Then he just, and then Al says it, and then everything just explodes, right? So.
But there is more than one way to turn off.
There is more, yeah. But this was more expected, right? So the timeline was telling us that we're getting there. So yeah, there is absolutely more ways to turn off. I'm obligated to say that we also do earth science stuff. I've been working interplanetary or deep space, and it's just been it's kind of funny. It's almost like we're broken up into who does what you like. I think it just becomes you get used to a certain way of operating. But we actually do a lot of earth science. One of the things that we do is try to actually make sure that Earth is protected, because we want to And then, but my main work has always been Mars. Unfortunately, I wasn't able to get, because we don't have a whole lot of material yet that we can release, because we're still designing. But I am working on the next Mars rover. Again, it's going to look a lot the same that you saw previously. It's a 2,000-pound rover. It runs off of a nuclear source. Actually, that's one of the main differences that we took with this Curiosity. It's a nuclear-powered rover, and what we use is we use the nuclear source as a heat generator, and then we use thermocouples to actually generate current that charge the battery, sort of trickle charge the battery at about 100 watts. So this is actually, if you were to look at it, it's actually a fairly low power system. We tend to use a lot of high gear ratios, so that we can actually get the power to climb and do other things like that. The Rovers, actually, the actuators to actually turn the rover wheels are about the same torque as about a Corvette engine. Per wheel. Yeah, we really gear them down. So the rover, if it could actually climb straight up a wall. It had that much power. But it's also running at 300 watts on average. So it's not less than your toaster. So that's some of the challenges that we have. Yes, sir.
Why do you have such a high torque ratio? Because you're not going to do that on Mars. It's just if you get stuck scenario kind of thing.
Yeah, right, exactly. So all of the rovers are, except for probably for the little one, these are all geologists, or rover geologists. So they're able to climb. They can actually climb some pretty heavy rock field, right? They can actually, and they use that torque to actually.
You're trading off distance for your torque.
Right. Yeah. Actually, the rovers move super slow, right? I mean, the way that the rovers are autonomous, and oftentimes when I have people come visit and we see the Rovers in action, first thing everybody tells me, like, why is it slow? And I say, yeah, you'd be slow too if I told you can either look or you can walk, but you can't do it both at the same time. And I told you to walk across the room, right? Well, the first thing you're going to do is you're going to kind of take a mental image of, okay, what's around me, and then I'm going to close my eyes and start to walk. Probably can end up walking a little slower just because I don't want to bump into something or fall, right? And then I'm gonna stop and okay, now I got to correct and I'm gonna go around. So the Rover, because the environment again I mentioned earlier, the environment's pretty harsh. There's a lot of radiation. The radiation can cause a lot of bits to flip and various other things, bad things to happen to electronics. So what we have to do is we end up flying older technology that's radiation hardened, so it's more immune to this stuff. When you do that, you tend to fly slower processor speeds, and so your iPhone, your Android is probably more powerful in processing speed than our Rover is. But we have to use the hardened. But your phone, take it up to Mars and see how long that thing lasts, right? So it's going to be one of those things. That's the trade, right? So we have to sometimes trade power or
So what is the nature of that hardening? Is it like a lead foil or just
pretty much? Some of it is just like it's just a vault, right? It's just a lead vault or pieces of lead material that go over. But also, it's in the chip itself. So a lot of things that we have inside are we call it triple mode redundant. So what they'll do is for every single bit, right, for a bit of something being on or off, it'll actually have 3 bits that check it. So if all 3 of them are 1, then it knows it's a 1. So if 2 are 1 and 1 flip, that means it's probably a 1, but something happened to this guy. If they're both 0, then they're probably 0 and the other one flipped, or they're all 0, right? So we're doing a voting method. So what happens is, if my capacity is now this big, but everything I do is in triplicate, right? My capacity just went down a third, so I can't, I have to deal with that.
So that has applications to Earth's cell phone.
Yeah, right. So and that's the other thing, right? Is a lot of times the things that we do, our algorithms that we design and build, are stuff that we might come up with something that says, okay, let's fix this problem. And then the next thing you know is you're using it as like a CD, right? Like for a CD for compression. One of the earlier missions that we had, which I didn't talk about, is Galileo. Galileo had an issue where when they launched it, they ended up launching late, and so they had to do I think it was a Venus flyby or something like that, and to actually get out to orbit. And they got a little too close to the sun. So when they got that close, when they deployed the antenna, it got stuck because something melted or something didn't work after the exposure. So we lost the amount of data that we can get down. So what the engineers did is we said, well, if we can't get the data down normally, why don't we compress it, make it smaller, then send it, and then we'll expand it on the ground. And so we started developing those algorithms, and then as you figure out that, hey, we can move a lot of data if we compress it down and bring it down. So what happens is that's technology that we then say, hey, industry, here's how you do some compression. And now that's how some of our work ends up coming out, right? I mentioned earlier, we're a FFRDC, a federally funded research and development. So everything we do is nonprofit. We're actually a nonprofit organization. So if a company comes and asks us to do something, we tell them, well, this is what it's going to cost. Because you got to pay for the lights and engineers and the parts on it. That's what it'll cost. But it's not because we're trying to make a dime on it. It's that this is what we think it'll actually cost. And because of that, right, our technology that we develop actually goes back out. Right? We don't necessarily hang on to it. There's some things that we'll keep, right, as intellectual property because we want to, again, stay competitive with other groups too. But we tend to work on the hard stuff. We try to leave the easy stuff to Northrop and Boeing. Anybody from Northrop, Boeing? Yes.
Do you encrypt transmissions and reception?
Yeah. We have different encryption methods, and they're like 12th order polynomials. They get up there pretty not that easy to break. That's why we're not too worried about it.
So the Ukrainians are not diverting Curiosity.
So that's funny, right? So we've had that a few times. Right? I've had friends of mine that said, "Oh, I heard that the Rovers got hacked," and I said, "Look, I have the dictionary. I know how to build the thing. I can barely operate it. I go, I doubt anybody else can do it by the fly." So I'm like, I'm not even worried about it. I mean, this stuff. I mean, we designed some autonomy into it, but the rover has to be commanded a certain way, and there's not a I don't care how good of a hacker you are, you're not going to be able to send a command to this thing of any use. Most of it's all restricted anyway until you're a certain mode. We know what that mode is. All right, if there's any questions, well, all right, let me pass the mic.
No. Can you explain how the next Mars mission is going to work with the 2 stages of getting the samples and then getting it back to Earth?
Yeah, so as I mentioned, I'm working on Mars 2020. And the way that's going to work is that it's actually a 3-stage process. Stage number 1 is the rover that's going to go there, and let me describe that system. So I'm working on the sample caching system, and my job is to make sure that as a subsystem, we work end to end. And what we're going to do is we have 2 robotic arms, one that's about a meter long, so about, is it a meter? No, a meter and a half. About a meter and a half long, and it's going to have a 45 kilogram turret at the end, so about a 100-pound drill at the end, a coring drill with some science instruments around it. Okay, so what's going to happen is, well, our responsibility is we're going to take a coring bit, we'll take a bit, and inside the coring bit, there's actually a tube, a sample tube that we'll put in there, an empty sample tube that will be added to the coring bit. And as we go and once the scientists determine which rock they would like us to pick or take, we'll then go and place the arm down, and we preload it down into the ground. So sort of like, you have a hammer drill at home, right? You want to get into the concrete or a brick wall, you kind of have to put a little bit of pressure behind it to get it to go in. We do the same thing. We have this arm that pushes down, and as we push down, the core will come out and start to drill. And it's a percussive drill, it's a hammer drill. So we'll be running at about 200 RPM and up to 30 to 40 hertz percussion, so how fast it's bouncing. And as it's hammering in, we actually have to go in and we start to take a sample. And as we get to the bottom, after we reach about 70 millimeters worth of sample, we take that tube that we inserted in the beginning and we twist it. And that twisting induces a shear load basically, like let's say at the bottom of this mic, and then it causes it to break. And then after that, we're holding it. Now the tube is no longer concentric circles, it's a little bit offset, so it holds the sample in there. Then we pull it out, we actually turn it upside down, and we do another bit of percussion. We actually shake it a little bit just to make sure the sample seats down into the tube. Then what we do is we actually come and dock to ourselves. We actually, on the rover itself, we actually have a place to dock and store our bits, right? So imagine, a carousel that has a bunch of bits in there for us to go and take samples with. So we drop the bit off now with the sample. The carousel now rotates in, and there's a smaller robotic arm inside that will pull out the tube and start to process it. What we're going to do is through a couple different checks. We have a volume probe that we'll actually go and measure to make sure we understand how much sample we actually did take. And then from there, we'll go take some images of the sample before we add a seal to it. And then when we seal it, we'll actually do a hermetic seal and put it, hermetically seal that tube. At some point later, we'll actually go and store the tube back, but at some point later, the scientists will decide they would like to drop off tubes. And we'll take a filled, hermetically sealed tube, and we'll essentially drop it onto the Martian ground. We're forward, right, and the next mission will come along. It'll be a small rover. We'll come along with a way to pick these things up. It'll go actually pick up the tubes and load them into what we call the orbiting sample. which is basically right now our concept is sort of this orb-looking thing that you kind of pull off in half, and then you put the tubes in there. Now our level 1 science requirement is 37 tubes. So we want to fill in 37 tubes worth of material, close this back up. That one will go on to a rocket that will do a remote launch off of Mars into a Martian orbit, where the third mission will come in. And the third mission we're calling it right now Nemo, next Mars orbiter. But we're calling it Nemo. Well, Nemo would actually be already orbiting Mars, and it'll pick up the orbiting sample and then bring it back to Earth. And then we all get to go to Texas, because that's where all the samples are going to, Johnson Space Center, and we can go see what they're doing there. But that's sort of the 3 steps that we're going to use to actually get these samples back. Number 1 is the first one that we got to do is actually get the sample, collect it, and then hermetically seal it and leave it for a future mission to pick up.
For landing the rocket that's going to take off the sample, what kind of method are you going to use to get that on the ground?
We're not sure yet.
Okay.
If I was to guess, it's probably going to be our sky crane. It's probably going to be the sky crane, but we're not sure yet. That's still in paper, pencil mode. We have some ideas and concepts, and we're working something. We have tested out what this orbiting sample will look like. What happens if there's a bunch of samples in this thing and it crashes on Earth? We've actually done some tests where we basically slingshot it down and let it crash onto the ground, and we want to see that we maintain the seals. We don't want to actually have anything exposed until it is exposed by scientists inside a controlled environment. So we're making sure of that. So we're doing little pieces of stuff that we're working on. Sorry.
So those samples that you said you're just dropping them on the ground, you're not afraid of not being able to find them again later?
Yeah, right. So one is we're not going to drop them on a hill. But yeah, no, we tend to have pretty good ways of locating where we're going to leave them. So we know where we're at, sort of longitude, latitude. But yeah, I mean that's probably number 1 concern, right? We've thought about it a bunch of different times. We thought about, why don't we leave them on the rover? But what happens if, when we get there, the rover can't turn on? Then we can't get our samples, right? What happens? Then they say, well, what if you just drop all of them at once? Yeah, but then what if something knocks them over, or something else happens on Mars that we're not aware of? Okay. So so we're going to do this sort of I call it a Hansel and Gretel thing. We're going to leave kind of breadcrumbs. And then we're going to sort of leave breadcrumbs throughout, because that gives us the most opportunity to come back and pick up the most set of things. Now the other thing we're doing is we're adding in some barcodes, so we can actually see what barcode, which tube we put out, and so therefore we know which tube it has what material. So if it ever comes down to it, scientists have to pick. So we have 37 that our scientists have said we need to bring back. We're taking 42. The difference is engineering failures. If something happens that we didn't quite understand at the time, so there's some that can fail. But if we get all 42, I can imagine the scientists are going to say, you're not leaving anything back there. It's all coming back, right? So it'll be a good problem to have if we can say we filled all 42 tubes and we're going to bring them back.
So the dust devils won't pick up the sample and move it?
They're not as, although Martian showed you that they're really strong winds, they are strong, but they don't have any real mass behind it to move anything. So and they're low to the ground too, so it won't be too bad.
And you don't expect them to be buried under sand dunes, or?
It'll take many years to do that, right? So if it was to, constant dust, yeah. So there's that, right? We are thinking about that as well. So the manipulator we have now that we're testing to pick up these tubes is actually driving into the sand a little bit, and kind of like your fingers might do, right? If you're kind of looking for something. So we're almost out of time here, so it's pretty quick. What I wanted to get to is, so JPL actually has probably the highest number of PhDs working there, right? So about a third of the engineering and science director, the area that I work for, there's about a third of the people are PhDs in some kind of science, right? And it's a lot of geology, but a lot of chemistry. So for the youngers in the group in the room, you know, any science, any math, any engineering, we do just about everything there. So if it's something that you guys really want to do, that's somewhere that you can get to do a lot of cool stuff. I mean, there's some days that I look to see what I'm doing and I'm like, really, they pay me for this? But I'll take it. One of the cool things that we've been working on is like I said, we try to do some hard stuff from time to time. So we have our Robo-Simian. And that's a technology demonstration, and that was a competition by DARPA who asked for us to make, or a lot of companies to make a robot that can actually go into a disaster area. And actually, you know, so the reactor that in Japan when it melted down, you know, they asked a lot of people to go in to sort of get it, you know, closed off and secured, knowing that they weren't going to live very much past that because of the radiation exposure, which prompted sort of this kind of thing, right? That sent robots in to do stuff. You know, so these robots are designed to actually go in and turn cranks and pick up drills and open doors and climb over a debris field, and it can actually drive a golf cart. So that's and that was it, getting ready to drive.
Is it safe to walk around the campus?
So is that a competition, and did JPL win?
Yes, it was a competition. We got to the next stage, and I think we came in fifth or something like that. We put the B team on it. We didn't. The rest of us were working on Mars stuff.
You like open houses where
Yeah,
see this stuff?
Yeah, open house actually is this weekend. However, all the tickets are gone. Unless you buy, they're free tickets, but because thanks to the Martian, we got a lot more people coming through, and we had to start. What happened was, I think one year when we weren't putting tickets out for people to come in, it ended up that people were showing up, driving from long distances and being turned away, saying we're at capacity, we can't let anybody else in. And so what we decided to do at least the last 2-3 years is that we put tickets out. They go, like I said, they're not on sale, but you're limited to like 4 tickets a person, a household, or something like that. And then what they do is that way you have a better, well, one is you're getting in, and it's a little bit more enjoyable because you're not just fighting over crowds. So I'd encourage you next year to look out for it. But yeah, that's when we kind of sort of put all of our toys out to let everybody see what we do.
Are they going to expand it so maybe more people can go?
Yeah, they've been adding more tickets, and so I think this year they put out 38,000 tickets, and those were gone. I think it took an hour or 2 for them to be gone. It's almost like a concert. We're all. In fact, half the JPLers don't get to. You have to now volunteer to work there so you can go. Yeah. So, but that's so we actually do have an open house. It's once a year. It just happens to be this weekend. Yes, sir.
How big is your guys' area, like where you work? And
if I remember the stats, like 176 acres. It's about the size of Disneyland. So,
How many buildings?
I don't know. We're up to, so it's one thing that if you get a chance to go there, you'll see that the buildings are numbered, and they're numbered in the order that they were built, not by any other logical thing. And we're up to like 349, but I don't know. But that means some buildings have gone up, some have come down, and from what I understood is that even that. If a building is proposed and NASA rejects it to say, no, you can't build it, that number is gone. So, hard to say, but there's probably, 100 buildings.
Yeah, and I assume you got small labs and big warehouses.
Yeah, it's all in between, yeah. Yes, ma'am.
What's the name of the company that makes that?
This is JPL. This is us.
Oh, it's under your logo.
Yeah. Oh, yeah.
Okay.
We built it. We designed it. The B team did, but we designed it.
What do you think of what SpaceX is doing?
I think it's great. I mean, they've launched a few of our payloads. But yeah, it's one of those things that SpaceX does launch vehicles, and there's no competition between us. It's we do the stuff on top of it. They get us there. But we enjoy it because actually, in fact, because of SpaceX, some of our missions are now getting a little cheaper because other rocket vendors are now pricing their rockets a little bit cheaper because they have to compete with SpaceX. So it's actually helping us out. They can put more of that money towards engineering. It helps us.
Do you think you use SpaceX technology to actually land future rovers and stuff on other?
We're very into our heritage. So our heritage tells us a lot. And so SpaceX would have to do a lot before we want to go pick up their stuff. We tend to have our ways of, the way we like to do things. There's call it the JPL way, and that's usually different than anywhere else. It's mainly because I mentioned earlier, right? We're non-profit. We're not. So all of our decisions are engineering based. They have nothing to do with making a dime. It's all based on engineering, and so that's typically what's the difference with the JPL way is that the CFO is there to.
But you still have budgets.
We still have budgets, absolutely. But I can spend all that budget. I don't have to worry about paying someone bonus, right? There's, I still have to make a decision on whether or not we do something or not, based on technical risk, not so much that a budget tells me I can't do that.
Plus, you want to have a high degree of confidence that once you get to the other end down there in Mars, it's going to work.
Right. Yeah. We also don't want to.
He's launching off Earth and landing on Earth.
Yeah.
Or not.
It's a little bit different.
Involve the budget and so forth. The mission that you're sending in 2020.
Yes.
Are you reinventing everything pretty much, or
no.
are you going to use like the basic
platform
that the Curiosity?
So we purposely, to make this mission affordable, we purposely are reusing. That's why I said it looks a lot the same. The cruise stage is the same. The descent stage, the powered vehicle is the same. The only main differences are the instruments, the payload, the science, and my portion, which is the sample caching system. So I'm working on sort of what the newest part of this rover is. And so what we like to say at JPL when we're talking amongst our colleagues is, they're all working to get my stuff on. So I appreciate all them working and doing it cheaply so I can spend it on myself. But yeah, we do have budgets. We still have to worry about that, but we tend to make engineering decisions more than budgetary. Yes.
Can you describe what the feeling is or the atmosphere the moment you know a mission is successful?
I still get goosebumps watching the video.
Oh,
yeah, it's incredible. I mean, we spend close to 10 years at some point on a mission, and so you see this from, inception all the way through. It becomes part of your life, your daily kind of thing, right? And then that's what I said. Sometimes I don't realize that I'm doing this stuff. So one time we were debugging an issue, and I had the rover up on like a jack, almost like a car, right, up on stands, and I was kind of climbing underneath and probing stuff, and okay, send this, and let's check the signals, and then, you know, someone looking at me like, you know, the jaw dropped, and I'm like, what? I'm working, you know? Yeah, and I didn't quite realize, you know, what I was doing. You know, I knew what I was doing, I just didn't realize sort of the gravity of it, right? You know, what everybody else was thinking. So, yes, sir.
Why is it important to have missions going to asteroids and meteorites? Is the same discovery?
No, it's different, right? So one of the things is, you know, we're trying to understand, you know, depending on, you know, which scientists you speak to, right? They're going to tell you different things, right? But early on, right? Early Mars was wet. It had an atmosphere, much like ours. What happened? So that's why some of the discovery is understand what happened. What are we getting to? Are we going to see the same fate, you know, over time, or is it, you know, or is this a big cycle that eventually will start to get warm again and wet again? So that's things that we're trying to understand. One of the things that we've tried to understand with like the deep space with Don, I'll tell you, I worked on a proposal that we'll see coming out in a few years. And we're going to the asteroid belt, and there's actually an asteroid that's all metallic. Now, what else can we think that's all metallic, right? It's our core. It's the core of our planet is molten. And now that one that's out there in the asteroid belt is all metallic. So what happened is, if that was a core that froze, that's the first time anybody's going to be able to study a core of a planet without having to worry about melting all your instruments. Right? So that's one of so that's why we're exploring, to see where things either came from or where they're going. And so it's just understanding that, you know, sort of that, those are our missions, right? We kind of push those boundaries. Right, well, I think we're out of time. Any last questions?
I have one.
Oh, sure. Yes.
When are we going to put men on Mars?
That's a tough one. So you know, with me doing the robotics and stuff like that, and I see how much what it takes to get there. We're making steps towards that way. One of the instruments that we're flying, actually the instrument that we flew on Curiosity, one was a radiation detector, and that radiation detector was on from the minute it was on the launch pad in Florida, all the way through Mars, and it continues to go because we're trying to map what the radiation looks like. You know, once we leave Earth and that magnetic field, the radiation gets pretty intense. So robots are okay, right? We can get the radiation. We have some bit flips that might happen from time to time, but we can adjust for that. Humans, not so much, right? We gotta protect the humans and radiation. So we can't fly a giant dead spacecraft because it's just too heavy to get off the ground and to stop it, right? We're not so worried about getting off the ground on Earth. We think we can do that pretty well. It's how do we stop on another planet? Especially when Mars is about 1% atmosphere it is on Earth. So that drag that you're coming in, it's way less. You don't slow down as fast as you would want to on Earth. So it's trying to slow that down. That's why we do the sky cranes. That's why we do these extra stuff to really try to get us to slow down. So we have to. So it's a tough question. I know the president and everybody has 2030. I'll say go for it. But I have a different. My view is a little bit skewed just because of I studied this stuff in every failure mode possible, so I know it's not that easy. The mission that we are working on now, Mars 2020, we'll have an instrument that can generate oxygen. So it'll take the Martian atmosphere and generate oxygen. Wow. So we'll be able to measure how much oxygen flow we can make. Now it's small, but it's something that we think we can scale up for a human mission. Questions?
When will you put a drone on Mars? Or flying drone?
So he knows. So he's prompting me. So that's one of the things that we're working on. Is we're actually working on a helicopter that's going to fly with us to Mars. And we're actually going to fly a little Mars helicopter. I think they're calling it Leonardo. and it's gonna fly, and it's gonna help do some recon for us. So what we'll do is, this thing will fly. It'll take some images, some high altitude images, send it back to us, and then we can help direct which way we want the rover to go. So that'll be the first time we fly a drone on a planet. Also with one of the things that I thought was kind of cool, I just came to that realization yesterday was, we're gonna make a tube, we're gonna seal it, we're gonna put a sample in there. It'll be the first time we can sample something on another planet altogether, and it's gonna be a whole new part number. And it's coming back, so that's kind of cool.
Is that drone gonna be piggybacked onto something, or?
Yeah, so the drone will be attached to the belly of the rover. We'll drop it off, we'll drive away, and then it'll kind of do its own thing away from us.
So it's on the same mission?
It's on the same mission, yeah. Yeah, so it's a little guy, it's not very big, but it'll be a helicopter that will fly around, and we'll actually have, we'll actually take a microphone, so we can actually hear from Mars what it sounds like on Mars. So that'll be kind of cool. That's one of the things. And then we'll have a couple new cameras to actually image or tape or video the landing. So the rover will get a personal view of this thing landing. During the video that I showed you earlier about the Curiosity landing, some of those images, some of the videos in there were actually real footage that we were taking. So we actually had a camera looking down, and you can kind of see how one, you see the heat shield fall apart, and then you can also see us coming down and approaching the ground. So that was actually pretty cool.
Do you know if that helicopter is going to be like rechargeable? Will be able to come back and charge off the?
So it'll be fully self-sustained. So it'll be solar panel. Yeah. So it'll work solar. It's only going to have a flight time. I think they're still working it out, but like 5 minutes or something like that, like every other day. Because one is we can't make it a really big copter, a big solar panel and stuff like that. It's going to be difficult to take. So you have to make it small enough to go, but eventually, it'll recharge itself. It'll have its own self-sustaining. Yeah, we try to make things kind of live on their own.
But it's going to have its own decision making, or?
Yeah, so I think that's the thing I don't know for sure is how they're going to tell it where to go. If they're going to have a crew plan, fly up 100 feet, do a scan, and then come back down. I don't know that yet. We're still kind of working those concept of operation. Yes, sir.
Where would you put the solar panels on the helicopter?
Right now, they're right on top. So basically, you have the rotor blades kind of sticking out, and then on top you have a disc, and that's where you have it. So you got it. So the hard part is, right, I mentioned earlier, Mars atmosphere is like 1% of Earth. So you have to actually change how these things, so the one is all of a sudden the rotors get pretty long, and any more weight that you put on there. So now you got to trade, now it's like, well, how long do I want to fly, and then how long do I want to charge the batteries? So now we have to play that game of, do I want to fly a long time, or do I fly less, but I can charge more often, right? So so those are all things that we have to do trades against, right? Understand which way we want to do. What's good for the mission? Yes.
How are missions proposed? What's the procedure like? Who is it presented to? What are the members of the?
Right, that's a good question. So the first thing that happens is there's this decadal survey. And what it is a decadal survey is a survey of all scientists across the globe. And they come across and they sit down and argue. And if you're ever in a room with scientists, like 10 scientists, and ask them opinion, you get like 25 different answers. It's pretty hilarious. But, so they'll sit there and argue. So what happens is they come up with whatever they feel the science community, when I say that is the world, feels that is an important thing to explore. So when they come up with that, they'll say, we think Mars is one, Europa might be another one, etc. They have their sort of ranked order. Based on that, we different centers and different companies for that matter, to propose missions to actually meet those science objectives. And then after proposals, if you show that, you can actually, one is you can do it, you have a budget that makes sense to what's lined up with Congress and et cetera, then you can actually pass all those gates, then they'll start to turn you on. But then they only do it for a little bit at a time, right? It's almost like every year we gotta get funding, it feels like. So we have to create a budget, and then they come back and they say, okay, well, there's these key decision points that they put in different phases. So in this phase, they'll give you some money, enough money to kind of work this part, and then that shows that you can actually put some more detail than your concept. And then they give you a little bit more money and show a little bit more detail. And then if you get through all that, then they say, okay, we think you're good enough. Now go ahead and build it and kind of go get it finished. And that's when we really kind of have to turn on the crank and get it going. But sometimes we're at the mercy of the budget. Then we have to sort of, move things around and get things working. Sure.
What's the name of the mission that just went between Saturn and its rings?
Oh, that's Cassini.
Okay.
Yeah, that's Cassini. That one's actually pretty cool. That was a lot of that technology that was developed there enabled Pathfinder to happen.
And then, how do you avoid unit conversion errors?
Sometimes we know. So we have our lessons learned document that we review, and now we hold a lot more reviews and check units.
The time frame of this 2020 project, when did it start through the thought process? When's it going to, are you in build yet, or when's it going to happen?
You're right. So 2020 is the hint on the date. So that's the year we're going to launch. It's going to be July-ish of 2020. This is when our launch window opens, and we typically have about 30 days or so in our launch window. And what happened, it's probably started, the idea of a sample return has actually been around since the early days of Pathfinder in the 90s. However, the concepts and ideas have been sort of developing slowly over time. I mentioned sort of budgetary things, right? Sometimes they give us money to do R&D, just research and development, not for a specific project, but just sort of prove some concepts out. And so that's been developing. I think probably in earnest when we really started working on this thing was probably about 7-8 years ago, is when we really started kind of nailing down the concepts of this thing. And so what we're doing now, we're in the build phase now. We're currently in the middle of building our design, finish our design, and starting to build our engineering units. After engineering units come our qual models, which allows us to rattle them, to heat them, to cool them, to kind of bang them around, and to show that our design is really going to work. And then we make our flight unit that we carry with kid gloves and don't get dirty, and we're not allowed to because we can't actually contaminate not only the samples coming back, but we can't put any of our chemicals on Mars either, right? We have to protect the planet, right? So there's this mission is actually going to be one of the first times. It's going to be an impressive way of how to get these things clean. I was talking to Kent earlier today, saying that some of the requirements that we have on our system, as far as cleanliness goes, as far as how clean, microbial clean it has to be, the method to detect the traces that they want us to be under, there isn't an instrument on Earth today that can measure it. So what I told them is that most likely what's going to happen is that scientists are going to have to get together to figure out how to actually do this measurement. And there's probably a new field of study that might come out of this in microbial chemistry and science, right? So this might spawn off a new field in the scientific community. So that's kind of the cool thing about what we do is that we don't know where some of our requirements or our technology is going to take us. It's going to, we're going to try to always advance as far as we can.
If you fall behind, you have to wait like 2 years to launch again.
Yeah. The orbital mechanics require a 2-year, roughly a 2-year slip. if we don't make it. Sure.
Yeah, I was wondering, is there any interest in exploring for and bringing back a sample of Martian water?
So we're not allowed to go grab the water per an international treaty. So we know where there's water, we know where it's can move, we're just not allowed to go get it. So until the science community and the Earth, everybody collectively says, go ahead and do it, then we'll go for it. Until then, we have to, we just avoid it.
So that would have to be resolved where you send people, right? You're not going to send that much water with it, you can't carry that much weight, right?
Yeah, what he's saying
resolved,
is
right?
bringing it back, right? Is more bringing it back. Is how do we bring it back? You know, I mean, we can, I mean, it can, part of it evaporates pretty fast in the atmosphere, so you have to figure out a way to hold it.
I mean, to keep people to drink once they get there.
Oh, yeah, we have, yeah. No, I think what he was talking about is actually taking a
right.
Yeah.
I'm asking a different question.
Yeah.
The issue about whether you can touch the water or not would have to be resolved before you can send people up.
Yeah.
Right? Or
Yeah.
you can make it out of the atmosphere.
We would probably want to make it out of the atmosphere, right? If we can generate oxygen, we can probably work to make water.
Is it because of impossible organism?
That's why, right? It's one of the things that I know we do pretty well is planetary protection and contamination control, right? Planetary protection, making sure we don't introduce any foreign, you know, I mean, obviously we're talking a rover there, right? But knowing what we actually, you know, that it's okay, but we don't have our, you know, oily fingers and our DNA kind of landing over there, right? So it's usually pretty clean, and we rely heavily on the radiation, right? The fact that the atmosphere is so thin. There's the sun, you know, the sun beating down, and it'll actually kill a lot of organisms too. But nonetheless, we still have to make sure when we get there, we're clean. It's best for doing. And then coming back now, it's going to be even. It feels like that's even harder now because now it would be the worst thing to actually get a sample from Mars and say, hey, we saw some DNA there, and it's like, well, yeah, it shows you that. Putting this thing together, right? And so we don't want that to happen. So we gotta make sure that. Yes.
When do you think we'll have an atlas from Mars?
What?
An atlas?
Like a map?
Like a map, the entire map.
We have pretty good maps now.
Yeah.
Yeah, I mean, right now, I mean, we're right now, one of the states that we're in for our project is that we're doing the landing site selection. Again, it's a collection of scientists. It's almost the engineers aren't really invited because they want to just focus on the scientific, the integrity of the scientific spot. And so later, once they decide where they're going, then they come and ask us, is it feasible to land in that area? And we can run our numbers and we tell them, yeah, we can. And so, but we have a fairly good.
For the entire country?
Oh yeah, we have, there's I think 3 or 4 orbiters right now that are constantly going over and imaging and I mean we have some really nice cameras that allow us we can actually see the rover tracks. From where they landed to where it's going, and you know, so that's kind of cool. So you can actually see, you know, the rover's like a pixel, but it's there. We've actually seen some of the European ones that have crashed, and we've found them for them, and that's what we've done. Yeah, so we've done that too. So we got some pretty good data, and yeah, from these images that they have, they're able to tell where water was before, and that's usually what they tend to focus on as far as wanting to land. Yes.
You have specialists in origami who help figure out how to fold
Pretty
things
much.
really small.
Yeah, we actually, the funny, you mentioned that, but we actually had a presentation and talking about origami and spacecraft, because yeah, they have to fold down into a very small package, right? Any extra mass that we have to, you know, we have to slow it down and we have to get it off the ground. So it's one of those things that has to be tight. You know, you don't necessarily want a bunch of air gaps in there because it doesn't help us. You know, more volume doesn't help us as much. But yeah, we spend a lot of time trying to get that and close clearances. I mean, we're talking sometimes. You know, we're looking at these drawings and the dimensions are in microns. So we're trying to get tolerances within, right? So we're actually really, really tight. And so that's what makes it the hard problem.
So you use a lot of nanotechnology?
Not as much, like the nanotube stuff. We have not for the Mars stuff. We're doing some other R&D kind of with that to see how good it is and strength wise. I think I mentioned before we're pretty much settled in our ways as far as heritage, and you know it's a really bad catch-22, right? But you can't find anything new until you've flown it before. So so you got to figure out how to get on some kind of research project or some kind of thing to actually show that it would work, and then anybody would trust it. But yeah, now like nanotubes is still, for our stuff, we're still a little bit we're letting it develop.
All these amazing approaches, from how to land on Mars to building a robot or hovercraft or mapping or whatever, is it more typically one person with an idea that he thinks through and then proposes it to a team? Or is it a team brainstorming session that one guy says, yeah, why don't we try an airbag? And another guy says, yeah, why don't we try 30 airbags?
Yeah, and it's more of a team, right? We going back to the JPL way, right? Typically is a lot of open discussion. We can get a little rowdy sometimes, but we're doing it for the sake of the project, right? So there's no hard feelings, because it's not, I'm not worried about someone checking my work because they think I'm not qualified to do the work. I've already proven that, right? It's that they're making sure that I've thought through everything. And so we typically have well, let's do it this way. Well, no, that won't work because of this, or so then it evolves. And it's still, I mean, even our design now, it's still evolving. As we drive into the details, like how do we do, it's one thing to say on paper, hey, this is your requirement. That's really easy to type. But to actually go off and do it, is a hard part. So sometimes we have to come back to the scientists and say, this is not going to work like that. We have to do it this way, or just to give you an idea of what the scientists told us. They said, hey, we want you to go take a core out of a rock on Mars, and oh, by the way, when you're hammering into a rock, we want it as solid as possible. Don't make it crack. But if you do crack it, make sure they're not more than 2 millimeters in size in the crack. And oh, by the way, try not to have any powder left in there, and don't heat the sample while you're doing it either. So. So now we got to get rid of friction, and we got to get rid of all kinds of other stuff, right? So now we have to build an algorithm for the robotic arm, just to, when it's putting the drill down, to know that if this rock is, and if you're not a geologist, which I'm starting to be a little bit, little bits and pieces here. So the rock, even though it's going to be hard on the surface, as you get down, it can change drastically in hardness. So if I'm hammering really hard up on top to penetrate the rock, it could be that I have to start slowing down as I get further down, but I wouldn't know that on the ground. So the drill has to know, based on sensors, on how to change that percussion level and the RPMs so that we don't break it as we go down and get a sample. So it's got to be smart enough. So you got to drill it smart enough to make holes. Yeah.
Is it possible the 42 samples is a reference to Douglas Adams' answer to the Hitchhiker's Guide to the Galaxy, where the meaning of life is?
No, I think we were at 43 and we took something out. No, actually we were less than that. We added one in. So it was less than that.
When you land the Curiosity rover that's down there, everything went great. How long do they spend looking at everything? They take telemetry all the way down and everything,
yeah.
I'm sure.
Yeah, so
evaluate that.
So the first 90 days is commissioning. So the first 3 months, roughly, was commissioning. And that was basically doing all the checks, loading a new version of software, getting everything kind of checked out and everything sort of exercise, right? Sort of your stretch on, wake up, right? Kind of get everything loose, see that it's all working. and then we go off and do it, and we start patrolling the mission. That's
I mean, after you've flown the mission, you must review it also to see if you, I mean, you probably learn things that don't work exactly.
Right. Oh yeah. We learn every day that something either doesn't work or either works well or doesn't work at all. Right? We learn and put it in the next one. In fact, the wheels that we're designing for this rover, although they'd be the same, they're not the same as the last one, because we found that the last ones had a design flaw that's been exposed. So now we redesigned it, did a better test, really beat up the wheels, and we're confident that now we got this problem here. But yeah, we try to learn. We learn from our mistakes. I mean, we know the stuff we're doing is not the easy stuff, so we try to learn and apply it to the next mission as best we can. So like the units, make sure we got those down. All right.
Last question. Do you ever sign them?
The what?
Do you ever sign the Rovers?
Spirit or Curiosity, I forget which one it was. I want to say Spirit. It was the one I was able to sign the cover before we sealed it up.
That's cool.
And then Don, one of the guy laying out the circuit boards put all of our names in copper on the side. That was fun. All right. Well, thank you guys.